Okay, good afternoon, all the students. We'll start our fifth lecture under this module 4. Okay, in the last lecture, we have seen how maximum likelihood hypothesis is used for predicting the probabilities. You know what is the maximum likelihood hypothesis, right? HML. If we write this HML as sigma I equal to 1 to M di log h of xi plus 1 minus di log 1 minus h of xi. This we have understood as the maximum likelihood hypothesis, right? Why do we use this? If di equal to 0, then we say that the hypothesis doesn't hold good with that particular training example. So whenever di is 0, this entire term will become 0 and this term will exist, giving the likelihood of that event not happening, 1 minus h of xi. But if you take di equal to 1, then the outcome of that training example is 1, indicating that the event has happened. In that case, this entire thing, 1 minus di means 1 minus 1 will become 0. So this entire term will become 0, and that will give you 1 into log of hi. Okay, so it is the probability of that event occurring. So whenever you take the training examples outcomes as yes or no, the event occurred and didn't occur, then all the lower probabilities you can decide a threshold, something like 0.5, and all the probabilities lesser than 0.5. It depends on the context. Sometimes your values all may be aligned only from 0.3 to 0.1. In that case, you can move your threshold to 0.7. But if at all your values are between 0 and 1, or your outcome label is 0 or 1, in that case, I'm talking both about classification as well as continuous variables. Categorical as well as continuous variables. Categorical means either 0, 1, yes or no, like that you have. Continuous values means you may have continuous values 0.1, 0.2, 0.3, 0.4. In both the cases, we calculate its probability. Okay, the outcome variable's probability. In classification, it is probability of 0 or probability of 1, probability of yes or probability of no. But when you are calculating, say, sale price of a house, in that case, the probability of the sale price being 1 lakh, or the probability of the sale price being 1.5 lakh, the probability of sale price being 2 lakhs, like that. It is continuous value, right? Now, when you're calculating those probabilities, all lower probabilities you can assign one particular class, all higher probabilities you can assign to another particular class. Say if you have decided a threshold as 0.5, then all the probabilities lesser than 0.5 you can assign it to negative class, and all the probabilities that are greater than 0.5 you can assign it to positive class. That is in classification. In the same way, when you're calculating continuous variables, you may have various probabilities calculated for the sale price, and based on those probabilities you fix a threshold. Lesser than this threshold, you say this would be the price range, and above this threshold you can put it into this price range. Like that, you can use this maximum likelihood hypothesis for predicting the probabilities of the outcome variable. Now in today's class, we'll see minimum description length principle. We have already learned about Occam's razor, right? In chapter 2. why you prefer shorter hypothesis over longer hypothesis, why you prefer simple decision trees when compared to complex decision trees. To understand that concept, we have quoted this Occam's razor method. This Occam's razor method is always we try to prefer the simplest solution when compared to a complex solution. Okay, so we have already learned about this Occam's razor, a popular inductive bias. Inductive bias means the assumptions we make, the bias we purposefully add to our experimentation. Say, when I'm taking Indian literates count, in that case, I may bias my work to only South India. Means I'm assuming that I'm assuming that more of the literates are there in South India, and because my time doesn't allow me to check the literacy population's literacy throughout India, I am adding a bias to my study. I'm adding bias to my experiment that I limit only to South India, or I limit only to half part of the India. Means I'm trying, no experiment will be designed like that, but for example, I'm trying to add some bias purposefully to my experiment. Means I'm trying to make some assumptions that most of the literate population in India lie in South India or in Central India. That is why I am limiting my study to this part of India. That is called as inductive bias. I am trying to add some partiality to my experiment. I am trying to make some assumptions about my experiment in order to make my work easier. Okay, so this Occam's razor method is a popular inductive bias. It is not that if you apply this, you will get a better result. Nothing like that. It is like an assumption to make your task simpler. Okay, so we we understood about this Occam's razor method as a popular inductive bias assumption that we have made, that can be summarized as how we understood about this Occam's razor method. Choose the shortest explanation for the observed data. Whenever you have set of explanations, best set of explanations, in that set always choose the shortest one, simplest one, less complex one. That is defined by Occam's razor. Now let us consider a Bayesian perspective on this concept. What is Bayesian perspective? Always you attach probability to every concept, right? In order to draw some inferences, rather than drawing them without any support, if you just add some probability so that you're making that statement with this much confidence, your statement, the probability of your statement becoming true is this much. If you assign such kind of measures, then it will be believable. The targeted audience feel that it is reliable statement that you have made because you have attached some probability with it. You have attributed to the chance, means error. If there is any error, that error has this much probability, but the overall result have this much probability. You are trying to assign some measure to indicate your confidence in making that statement. Did you understand? That is what is called as Bayesian approach to draw the inferences. You're trying to attach probability to your conclusions or the statements made. That will indicate your confidence in making the statement. Now let us consider a Bayesian perspective on this concept. Now let us attach this Bayesian perspective to this minimum description length principle and see how better we can understand this particular topic. Okay, now let us consider a Bayesian perspective on this concept and a closely related principle called the minimum description length principle. In the name itself, you should be able to recollect something. When I say simplest hypothesis should be always preferred, and when I also say minimum description length principle, what does it indicate? Minimum description length you are trying to prefer. The description about the hypothesis, if it is minimum, you are trying to prefer that particular hypothesis. Okay, now you are able to find the relation between these two. Occam's razor and minimum description length principle. And now if we associate this with Bayesian perspective, let us see how better this topic can be enhanced. Now the minimum description length principle is motivated by interpreting the definition of HMAP. What is HMAP? Maximum a posteriori hypothesis. Means you have lots of hypotheses, but which hypothesis has the maximum probability of being true with the set of training examples given, which is consistent with the training examples given. That is called as your HMAP. You may be having 2 to 3 hypotheses, but one hypothesis will have the maximum probability, maximum likelihood, say 75%. Only that hypothesis will become your maximum a posteriori hypothesis. What is maximum a posteriori hypothesis? The probability of H becoming true for the given data, for the given set of training examples. This is also called as posterior probability, and that hypothesis is called as maximum a posteriori hypothesis. Got it? Now let us understand this in the light of basic concepts from information theory. Now consider again the definition of HMAP. You remember the definition of HMAP? It is argmax for all the hypotheses that belongs to the hypothesis space H. It is the product of probability of D given H multiplied by probability of H. How did you minimize this formula? You remember initially you have probability of H given D as probability of D given H multiplied by prior probability of H divided by prior probability of D. But prior probability of D doesn't have any effect, means it doesn't vary. If only prior probability of D is taken, it doesn't vary with respect to hypothesis. Means it is a constant. That is why we are eliminating that term and taking only the terms in the numerator. And our motive is to, our objective is to maximize this multiplied term in order to get the maximum likelihood hypothesis, in order to get the maximum probability hypothesis, which is called as maximum a posteriori hypothesis. That is why we have written as argmax. Among all the hypotheses in the hypothesis space H, your objective is to maximize the product of probability of D given H multiplied by prior probability of H. That will become your maximum a posteriori hypothesis HMAP. Okay, which can be equivalently expressed in terms of maximizing the log 2 term. Now let us apply log to this. Let us apply log to this particular formula of HMAP. So this becomes HMAP equal to argmax of H belongs to hypothesis space H. When you apply log, what will happen? Log of m into n. If you apply log, you can write it as log m plus log n. In basic logarithm chapter, you might have come across this. If you have log m by n, you write it as log m minus log n, right? So you have here product. That is why when you apply the log, you get log 2, you are taking it to base 2. Did you observe nowhere we have taken base 10 logarithm in our machine learning? Always we take it as base 2. Why? Because we are working with binary data. Now log 2 probability of D given H plus log to the base 2 prior probability of H. Okay, this is how the HMAP equation have been transformed after applying logarithm. Is it clear till here? Or alternatively, minimizing the negative of this quantity. You are maximizing a positive quantity means, other way how you can say, you are minimizing the negative quantity, right? Say when I say minus 2, I'm trying to minimize this means I'm making it as -1. I'm trying to minimize this means I'm trying to make it as 0. When I talk about it the other way, I'm actually maximizing this values, right? I'm trying to increase the value from -2 to 0. I'm trying to increase the value of that number. In the same way, when you are maximizing a positive quantity, it is nothing but minimizing its negative quantity, right? That is what we have done here. H map equal to your minimizing, instead of argmax, now you have taken as argmin and just applied negative symbol. That's all, nothing else. So when you multiplied this entire equation with negative symbol, you get minus log to the base 2 probability of D given H minus log to the base 2 prior probability of H. It is very straightforward, right? There is nothing here, no hidden derivations here. You have taken the maximum a posteriori hypothesis formula and you have applied log to it, but maximum a posteriori hypothesis is to maximize the likelihood of a hypothesis, or in other way, you are minimizing its likelihood when you apply a negative symbol, negative likelihood. Okay, so that is given here. Now it can be interpreted as a statement that short hypotheses are preferred because we are using argmin. Because you are using argmin, H belongs to H, and you are minimizing negative of something. How it can be interpreted? It can be interpreted as a statement that short hypotheses are preferred. Short, minimum of something you are preferring. Minimum of this hypothesis you are preferring. You are trying to minimize something. That can be expressed as a statement that short hypotheses are preferred. Simple hypotheses are preferred. Okay, now consider the problem of designing a code to transmit messages drawn at random, where the probability of encountering message I is Pi. Understand carefully. Now let us consider a simple problem. Say in olden days they used to send telegrams, right? For that they used to use this Morse code. Rather than sending the text, they used to use the Morse code. Means they just press, for each letter there are some specified number of dots. They just press the machine to apply those many dots so that it can be decoded on the other end, on the receiver side, into text again by seeing this code. So this code can be transmitted easily rather than the text. That is why they have preferred this Morse code. Now, in our case, let us assume that it is less cost is involved in order to send shorter codes rather than longer codes. Okay. Now consider the problem of designing a code to transmit messages drawn at random. We don't expect that this message would come. We are drawing it at random, where the probability of encountering message I, let us talk about one single message I. What is the probability of encountering that message I when the messages are drawn at random? It is P of I. Right? Remember, the notation is P of I. Now we are interested here in the most compact code. As I said, that will be cost effective. Why? Because rather than transmitting large codes, it is cost effective to transmit smaller codes, right? So in this case, we are only interested in most compact. Compact means smaller, lesser, less lengthier codes. Okay. Now to minimize the expected code length, in order to reduce the code length, we should assign shorter codes to messages that are more probable. Means, say you're creating a dictionary for this coding. Now you see which messages are more probable. See, in olden days when telegrams are sent, normally most of the telegrams have somebody serious, start immediately, or getting operated, start immediately. Emergency, start immediately. Most of the telegrams contain start immediately. That is what telegram is intended for, right? In order to convey some emergency messages. Now, most of these messages contain start immediately. So that in that case, when you're creating a dictionary of the terms and the Morse codes, you can assign shorter codes to start immediately. So that immediately it can be, quickly it can be transferred with lesser cost. Did you understand? When we assign short codes to start and immediately or start and quickly, if you assign shorter codes to them, transmitting the short codes will be easier, cost effective, rather than transmitting longer codes. So the most probable words, if you are taking in the telegrams, assign them shorter codes so that they can be cost effectively transferred. And other words which are rarely occurring, you can assign longer codes based on convenience. Okay, so to minimize the expected code length, what do? We should assign shorter codes to messages that are more probable. Messages that are more probable, assign shorter codes to them. Like I said, start immediately. Assign shorter codes to them because those two are more probable in most of the telegram messages. Did you understand the context now? I'm not at all talking about telegram, but in order to make you understand this scenario, I'm giving that example. Okay, don't completely go into that particular example. I'm just giving you how words can be, messages can be encoded in order to transmit them cost effectively. Right now, this is one theory. This is one concept in information theory, assigning shorter codes to more probable messages. Now, the optimal code, that is the code that minimizes the expected message length. Optimal code means what here? The code that minimizes the expected message length. The message length can be brought down to be simpler and simpler in order to send it cost effectively. That is called as an optimal code that you prefer. Now the optimal code assigns minus log to pi bits to encode the message I. Say there is a message I. Now what is the probability of that message that can be encountered frequently? For that you are assigning it a negative log to the base 2. Okay, assign this. Now we will refer to the number of bits required to encode the message I using the code C. We'll take this term to refer to the number of bits required to encode the message I. Okay, C is the number of bits required to encode the message I. Its probability is pi. Now we'll refer to the number of bits required to encode message I using code C as the description length of the message I. Now we call C as the description length of the message I with respect to C. That we denote by using LC of I. So when I write LC of I, it is the description length of the message I with respect to the encoding C. C is the number of bits required to encode message I, remember. Okay, I'm reading this once again. When we write LC of I, we can read it as the minimum, the description length, not minimum, the description length of message I with respect to C, where C is the number of bits required to encode the message I. Now, what is our objective here? To minimize this length as much as possible in order to transmit this message cost effectively. Did you understand? Our objective is to reduce this encoding message encoded message length for the message I, so that it can be easily transmitted, cost effectively transmitted. Now let us take this formula, that is maximum a posteriori hypothesis formula, in the context of minimum description length principle. This is not actually our formula for HMAP, right? But we have molded it so that it will suit the explanation of minimum description length principle. We are minimizing something. Our hypothesis is to minimize something here. What we are trying to minimize? We are trying to minimize the length of the description. We are trying to minimize the description of the hypothesis. Now let us interpret this equation according to the above result from the coding theory. Let us take the context of the coding theory, information coding theory, and understand this minimum description length principle. Now log 2 P of H minus log to the base 2 P of H is the description length of H. Now instead of message I, we slowly transform that to suit our context, that is hypothesis. What is our intention? To reduce the length of the hypothesis, to make the description of the hypothesis as simple as possible. That is why instead of message I, we now transformed it to H. Our objective is to reduce the explanation of this H, make the hypothesis as simple as possible. Okay, so minus log 2 P of I we used before when it is message I, but now you are reducing the description length of the hypothesis. That is why you have used negative minus log to the base 2 P of H. It is the description length of hypothesis H under the optimal encoding of the hypothesis space H, capital H. Now from H, hypothesis space H, you take the hypothesis and you are trying to prefer the hypothesis that have minimum description length. Simplest representation of the hypothesis you are trying to prefer. Now in our notation in the previous slide, can we write it like this? LCH of H equal to minus log 2 P of H. How do you read this? The description length of hypothesis H by using the encoding technique C from the hypothesis space H. Understand this carefully. I am reading once again. The description length of the hypothesis H. L is description length. The description length of hypothesis H by using the encoding technique C from the hypothesis space H. How do you represent? By this minus log 2 P of H. Minus is given here. Do not get confused. Okay, this minus, yeah, I'm putting here. Minus log 2 P of H, where CH is the optimal code, encoding code for hypothesis space H. For the hypothesis space H, you have assumed an encoding technique. Using that encoding technique, you have encoded all the hypotheses. Now, among them, which hypothesis is having the simplest encoded description length? That will be your minimum description hypothesis. Simplest hypothesis that you are preferring according to Occam's razor method, Occam's razor theory. Did you understand now? Now, minus log to the base 2 probability of D given H. What is this one? We have seen probability of H, applying log to prior probability of H. Now, probability of D given H, applying log to probability of D given H. It is nothing but the description length of the training data D given hypothesis H under this optimal encoding. Taking the same optimal encoding C over the hypothesis space H. Are you following? Taking the encoding technique C for the entire hypothesis space H, you are applying log to probability of D given H. Now, Did you see slowly you're transforming Bayes theorem into maximum a posteriori hypothesis, and maximum a posteriori hypothesis, you're again transforming it to minimum description length context. So you have got the representation for P of H. Now you are representing P of D given H also. Therefore, we can rewrite above equation, that is this equation, to show that H map is the hypothesis H that minimizes, because it is argmin, you are trying to minimize the description. H that minimizes the sum given by the description length. Here you can represent it as sum. If you take the minus out, you can represent it as sum, right? Now, therefore, we can rewrite above equation to show that maximum a posteriori hypothesis is the hypothesis H. Which hypothesis? That minimizes the sum given by the description length of the hypothesis plus the description length of the data given the hypothesis. Got it? Finally, you are able to write it in terms of hypothesis and D given hypothesis, means training data given hypothesis. You are able to express this H map in terms of minimum description length principle. Your job is done, right? Now, how you are writing this H map, argmin, H belongs to H. How you are writing this? Minus log 2 P of H. See, when you are able to write probability of I as LC of I, probability of H, can't you write it as L of C probability of H like this? Instead of probability, you are taking only the length of encoded value. That is why instead of P, you are using L. Okay, here you are writing probability of I, you have written it as LC of I, indicating the length of message I when encoded by using this encoding technique C. Now, when you take probability of H, you can write it as the length of the hypothesis by using this encoding technique C over the hypothesis space capital H. How do you write it? L C of H. What you are encoding? The hypothesis small h that you have written here. Okay. So instead of this term minus log 2 P of H, you have written it as LCH of H. This L is the length of the hypothesis using the coding technique, encoding technique C, over the hypothesis space capital H. Did you understand the term clearly now? Plus, now you are writing this in description length terms. This term you are writing in minimum description length terms. So how do you write that? Plus length of the hypothesis, the probability P of D given H, that is written as length of D given H by using the technique C over all the training examples given the hypothesis is true. Okay, that is your second term. Now your maximum a posteriori hypothesis, this one you are able to represent in the description length format. Is it clear now? What happened to this minus? Minus is nothing but you're representing that you're trying to minimize that negative term. Now that minus, you have represented it with the minimum description length. This negative term, negative means minimum, right? Now this negative term also you have represented using the minimum description length. That is how negative sign has vanished here. Do not get confused. Okay, so your final equation is maximum a posteriori hypothesis when represented in terms of minimum description length. It can be written as argmin H, length of the hypothesis using encoding technique C over the hypothesis space H, this term, plus length of D given H when this encoding technique is used to encode D given H. Okay, this is called as your minimum description length principle. The minimum description length or MDL principle recommends choosing the hypothesis. What type of hypothesis? That minimizes the sum of these two description lengths. If it minimizes this term and this term added together, that will give you the maximum a posteriori hypothesis, which is having minimum description length. You understood now? Maximum a posteriori hypothesis means the maximum likelihood hypothesis. The best solution you are searching for is nothing but the minimized length of description for this hypothesis. That is minimum description length principle. Is it clear, students? Maximum a posteriori hypothesis, or the hypothesis that would have maximum likelihood, is nothing but the one which has the minimum description length, which is the simplest hypothesis. That would be preferred as your maximum a posteriori hypothesis. Nice explanation, right? So that is given in this point. The minimum description length MDL principle recommends choosing the hypothesis. What type of hypothesis you are trying to choose? That minimizes the sum of these two description lengths together. If it minimizes, that will be your most probable hypothesis. That would be your best hypothesis you are searching for. That would be your simplest hypothesis you are searching for, because you prefer simpler solutions over complex solutions. Simpler solutions are here represented by argmin. You are minimizing the description of the hypothesis to make it as simple as possible and to make it as the most probable solution for your given training examples. Got it? Now, assuming we use the code C1 and C2 to represent the hypothesis and the data given the hypothesis. Assuming we use code C1, C1 is to represent your hypothesis H, and C1 is to represent your hypothesis H, and C2 is to represent your hypothesis, your data given hypothesis H. We can state the MDL principle as, how do you represent now? Simply HMDL equal to minimum description you prefer for the encoding that you use for the hypothesis H plus the encoding you use for hypothesis D given H. Okay, so these two terms you are trying to minimize in order to get the minimum description length principle. So instead of HMAP, you are using HMDL because you are actually talking about a most probable hypothesis in the context of minimum description length principle. Instead of HMAP, we prefer writing HMDL. Now this HMDL is nothing but minimizing the length of description of H using the encoding technique C1 and minimizing the length of D given H using the encoding technique C2. Okay, that will give you minimum description length hypothesis. Now this above analysis shows that if we choose C1 to be the optimal encoding of hypothesis CH, and if we choose C2 to be the optimal encoding for CD given H, then in that circumstances, in that situation, your hypothesis minimum description length hypothesis is equal to your maximum a posteriori hypothesis. Means your intention of reducing the size of hypothesis, description of your hypothesis, is nothing but finding out your maximum likelihood hypothesis, which is of shorter length, which is very simple to understand. which is very simple to implement, which is very simple to be noticed with most of the training examples. Okay, that is your HMDL, which is your HMAP. You are trying to search for something which is simple. You got that, and that is your preference as your HMAP. Okay, thus the MDL principle provides a way of trading off hypothesis complexity for the number of errors committed by the hypothesis. Again, interesting concept here. MDL principle provides us a way of balancing hypothesis complexity for the number of errors committed by the hypothesis. Say, if the hypothesis is very complex and it is committing very less errors, do you prefer such kind of hypothesis or simple hypothesis which are making a moderate number of errors? Which one do you prefer? According to minimum description length principle, you have to prefer hypothesis which makes nominal amount of errors, simple hypothesis which makes nominal amount of errors, rather than complex hypothesis that works very well. That is the notion behind this minimum description length principle. I'm repeating again, you have two options. One hypothesis, simple hypothesis, making some errors, and another option is complex hypothesis, which is very perfect. Which one do you choose? Always, according to minimum description length principle, you have to prefer to choose simple hypothesis, it making nominal amount of errors, not a problem, because this simple hypothesis would be able to generalize well for the new data or unseen data, rather than complex hypothesis not committing at all any errors, but its generalization capability will reduce as its complexity increases. Okay, that is the example of overfitting. Right? So see the last point, it might select a shorter hypothesis that makes a few errors, yes, over a longer hypothesis that perfectly classifies the training data. Though a longer hypothesis perfectly classifies training data or predicts something perfectly, that is not preferred actually, because it results in overfitting. It can't generalize well with unseen data. That is why we should always prefer shorter hypothesis that makes nominal amount of errors, no problem. Okay, because that will have good generalization capability compared to longer hypothesis that doesn't make any errors. Okay, this is the idea behind minimum description length principle. You are trying to minimize the description of the hypothesis as simple as possible so that it can generalize well to unseen data. I have made this concept as simple as possible in this PPT. Okay, so for this presentation in the exam, you can refer to the PPT, and for in-depth knowledge, you can refer to the textbook. Now, in the next class, we'll go through the next concept, naive-Bayes classifier. Any doubts, students, still here? Students, you have any doubts in today's class? You want me to repeat any concept? How maximum a posteriori hypothesis, how it has been slowly transformed to minimum description length hypothesis by using encoding technique. Did you understand clearly? Okay, then we'll meet in the next class.